YouTube doesn't care. And if we're just performing for Taylor, what does it really matter? Actually, we're going to be kind of doing this video for Miss Megan, right? And Scott. Treat man. Okay, so yes, or on Monday we talked, or Tuesday. No, Tuesday you took the test, right? Okay, so Monday we talked about linear approximations. Today we talked about differential. So I'm going to draw a gentle curve, and I'm going to draw a tangent line to that curve. A gentle curve. This is not a gentle curve. It's like a variation of the barcode, you know. Yes, that's a violet curve. Thank you. Okay, so we have this function, and I draw the linear approximation of the function. We got y equals f of x, and our linear approximation will be y equals L of x, which we gather from the derivative. So this will occur at point x. And what we're going to do now is differentials, they approximate change. And they approximate change in the y values. So if I go over a certain x amount, we will call it change in x, which is, what is that triangle letter? Delta x is change in x. And we will call that the same thing as dx. Delta d, very good. We have two corresponding values. This green line would be the change in the y value of the function, correct? Delta y. But that change in the function is different than the change that we expect from the derivative or the rate of change function. So you can see that the red would be dy. If you can't keep up now, don't even try next year. Just drop out. Good, yeah. Excellent. All right, thank you, Kimball, for your expertise. So, the differential we will refer to as the dy. Now, why is this valuable? Delta x is the same as dx, but dy is not the same as delta y. But within close intervals, dy approximates delta y. Do you all agree with that? Yeah, I mean they're close within a given interval. You know, for example, if I don't go quite over that far, let's say just go over here, and all of a sudden you see that delta y and dy are very close, aren't they? So that's the amount of change, yes. We would expect that our estimation would be even further off, but we don't have a prediction about how far off because this is always linear, and we don't know this behavior. This might be, in some cases, exponential. In some cases, it might be a polynomial. We don't really know. So all we know is that we like to be close. That it's a better estimation if we're close. So we come up with this formula, dy over dx. What that means is the derivative of y with respect to x is the same as f prime of x. Everybody agree? Well, we want to solve for dy, so what would you do? Yeah, so dy is f prime of x dx. That's a differential. Differential has great applications. In fact, this would be the very beginning point of your topic differential equations, or the topic in college called Diff-EQ. You were taking Calculus 1. You could take Calculus 2. We'll actually do a little bit of Calculus 2 during this course. But some people would say Calculus 3 would be multivariable calculus. Some people would say Calculus 4 would be differential equations, or Diff-EQ. Another calculus would be, say, analytical or complex calculus, which is a theory course. So you can take a number of types of calculuses. Generally, we regard them as three: Calc 1 and Calc 2, and then multivariable calculus, which is Calculus 3. Differential equations does involve calculus, but also involves other topics. A lot of physics and a lot of linear algebra involved in there as well. So find the differential dy and evaluate dy for the given values x and dx. So I just used my formula. Dy is equal to f prime of x dx. My function says 3x minus x to the negative 1. Everybody agree I can write it like that? So the derivative of y will be dy equals 3 1 over x squared times dx. This is my differential. Do I know the x value? What is x? 2. So you have dy is equal to the quantity 3 plus 1 over 4 times 1/2. What is 3 plus a fourth? 13/4 times 1/2 is 13 over 8. So that is my dy. That is the increase in the y value, the approximate increase in the y value. Any issue with that? Okay, you try the next one on your own. We keep trying, we figure out more and more. So what you should come up with is dy is equal to, this derivative is negative 3 over the quantity x plus 1 squared times dx. That's my differential. And so dy would be, if you plug in 1, you get negative 3 over 4 times 1 over 100, or negative 3 over 400. Did anybody raise a decimal? What did you get? Okay, we don't have a lot left that we have to do. We have to do this problem. We have a couple on the back side. You'll be able to work on your homework. So, yes. 20. So, we'll for sure get through example 4 here. Example 4 says compute delta y and dy for the given values of x, and sketch a diagram showing the line segments with lengths dx, dy, and delta y. I'm going to start by sketching the graph. This is so that you understand what the heck it is that you're doing, okay? So I was a person, when I was in mathematics, I wanted to see it visually. We thank Descartes and other people for putting mathematics on the coordinate plane so we understand what's going on. Y equals x to the third plus 1. What does a cubic look like? Okay, and if it's plus 1, it's shifted up 1 unit. So we could graph this function pretty easily. With just a little bit of knowledge, this is going to go through negative 1. Hopefully your pre-calculus teachers taught you something about polynomials and functions. I would put in a complaint about him. I'm going to do something that will make some of you angry, but um, I'm not going to call that 2. What is the change in x? What's my delta x? 0.2. So I would be moving from the coordinate 1 over to the coordinate 1.2. So I know that that's not evenly spaced, but for the purpose of our drawing, I'm going to do that. So it says our x value of 1. Oh, I'm sorry. If I plug in 1, what output do you get for this function? 2. Sorry. Thank you, Luke. I know we can always trust you to do the right thing. Free. do I have to answer that? Gosh. All right. Oh. Oh. This will be so. Fifth hour. All right. So, that's my tangent line, and that's a linear approximation. And within close intervals, we can also estimate the change. And so, as you look here, as I go from 1 to 1.2, what is delta x? 0.2. Now, here's the important part that you need to learn for today. As you move up to the function, that is that delta y or dy? Do you know? That is delta y. Okay, we'll start when you get back.